Professor Thiago, Silveira, and Professor Cláudio Jung. The floor is yours, so please get started.
So, good morning, everyone. Thank you for the presentation, Manuel, for the introduction, actually. Okay, so here we have some QR codes, and you can check our websites. And here we have our first spherical image, where, wait a minute, here, me and Professor Cláudio appear, and we will discuss a little bit more on this kind of signals throughout this talk, okay? So here we have just an agenda. It's divided, the presentation is divided in two parts, though we will have a full-time presentation. We will not break the presentation in two. First, we get an introduction on this subject. So we were asking ourselves, what are 360-degree images? Where do they apply? If they, we want to know if they differ from traditional images, and what is the impact of this difference, if it exists. Then we move for the spherical image model, and we will understand how can we model a spherical camera and understand mathematically how the spherical image is formed. Then we will talk about acquisition devices and representation formats. Specifically, we will deep in catadioptric, holodioptric, and fisheye-based systems. And we will talk about a bit on some of the most representative formats. Then we move for the main challenges of spherical images. We will understand what we call here the FoV dilemma. Then we understand what are the challenges in the rectangular format and other representations. We'll talk a bit on visual distortions and benchmarking, and then we will move to three selected applications that are gravity alignment, layout estimation, and depth estimation. And then we'll close this talk with final remarks. Okay. So first of all, we need to understand what are actually 360-degree images, and I think that the most straightforward way to think about them is to think about a Christmas ball. So if we look at a Christmas ball, we will see ourselves, and most of the context around us. And as we move around this Christmas ball, we will see more and more information. So of course, our eyes are seeing what the Christmas ball reflects. But if we think we are the Christmas ball, we will see everything around us. So everything that's on the surface of this Christmas ball is some kind of an intuition of the spherical image. Okay. Well, we will exchange words as synonyms, and to be clear enough here, we add this bullet. So we will call 360-degree images as unidirectional images, spherical images, and panoramic images as well. Okay. What's the main characteristic of a spherical image? Well, its main characteristic is that any spherical image stores the information from the whole scene where it was captured. So everything in the scene is represented in one single image, and this image is what we call a non-directional image. Why should we pay attention on spherical imaging, and why we are having this talk now? So 360-degree vision is becoming very popular nowadays, as we have affordable devices for capturing and visualizing this kind of signal. So we will see next that we have some kind of devices for capturing, and some of these devices were invented decades ago, but now we have more interesting device, let's say, that we have widespread for the community. 360-degree media approximate what we call the planoptic function, which is utopic function, utopic imaging model, or an ideal imaging model, where we can capture all the scene information from every position in the world coordinate system a long time. So 360-degree media capture the complete scene information a long time if we're talking about videos, but of course we cannot capture this information from any position. So we have to position to locate the camera in the different parts of the world to capture this different data. Okay. So where 360-degree images apply, and we can think that actually it can be applied to every visual computing task. Of course, we have some of these applications in mind that we look at the application and say, oh, this is a classic application where 360-degree images can be applied. Some of them are robot navigation, so we can understand that a robot that sees everything can navigate in the scene with a much more safety and do what it is meant to do. Also, we can think about surveillance. So we have one camera that doesn't need to choose where to look at, but it sees everything all the time. We can also think about autonomous driving systems, and we can, again, imagine that seeing everything can be, important to this driving system, as it will not do what it should not do. And one of the most common applications are in area of AR, augmented reality, mixed reality, and virtual reality, where the users use this kind of device for visualization. And here we have some immersive experiences in places captured with spherical images. Of course, we can think about many other applications, and we'll discuss some of downstream tasks in this talk later. So the first question that appears when we think a little bit more on spherical images is how it is defined and how it differs from what we will call here traditional images, or those images that were modeled as pinhole from pinhole cameras. So the first thing we need to rewrite here for you is what we saw, that camera sees everything. We will now call it as the camera has what we say full field of view. So it sees everything, so we have a full field of view, and we call it FoV. Here we have a regular camera capture, and here we have a spherical image capture from the same scene in the same position. And we see that, well, these two images are not similar. This regular camera has a narrow field of view and captures a portion of the scene, and the spherical camera has a full field of view and it captures everything in the scene and maps it to a sphere. So the data acquired from a camera, a spherical camera, is mapped or is represented on the unit sphere. And one thing we need to state here is that 360-degree images are not 3D images. So this is a misunderstanding that commonly appears when you're talking first time on spherical images. This will be more clear as we move on the presentation. And the question is, how can we process spherical signals once we are not representing our signals on the plane as those traditional images? Before we move to the processing, we should first understand how a spherical image is captured, actually. So we have here what we call the spherical imaging model, and it bases on what we know as central projection and spherical projection. So central projection is also applied or also considered in pinhole imaging. And the basic idea is that everything in the world is projected to plane in the pinhole case, or an sphere in the spherical case, that is centered on, you know, a 3D point on those world coordinates. The spherical imaging model abstracts the cameras as a sphere that sees the surrounding 3D world. Okay, so it goes in the same vein as we saw before. But the spherical model actually understands a spherical camera as a unit sphere. Okay, and everything in the world is projected to the surface of that sphere using central and spherical projections together. Unlike the pinhole imaging case, we have only the extrinsic parameters. So we have only 6 degrees of freedom, 3 degrees of freedom for the translation of the camera, and other 3 degrees of freedom for the rotation of the camera. So it's actually a sphere that can translate and can rotate around itself. So let's understand this concept in baby steps. First of all, let us define what we call a 3D world coordinate system. And, well, it's arbitrary. You can define this world system whatever you want. First of all, we need to define its center, okay, or its origin. And then we can think about the other points in the world as somehow parameterized by this world coordinate system. Okay, so we have here an example of an X 3D point or world point. Okay, then we can think on our camera as a unit sphere, and we can think that this sphere can rotate, as we talked before. Okay, if we assume that this camera is aligned to that world coordinate system and centered at this world coordinate system, we have this simple formula for projection. So basically, this 3D world point is projected as an image point that we call here on the surface of the sphere, and it has like a unit norm. Okay, basically we divide this vector by its norm. Okay, well, we know that the camera may not or might not be centered at this world coordinate system, and actually might not be rotated or aligned to this world coordinate system. So we need a more complex, not so much, equation to describe these imaged points as function of the camera rotation and the camera center. Okay. Well, just for record, we will use this translation vector notation that some kind of induces the center of the camera. Okay. In terms of representation, we see that this camera is aligned to and centered at the world coordinate system, whereas this other camera is not. Okay. Well, just one thing that we need to understand here is that what we image here, what we record here, is actually the color or the intensity of this world point, right? And this can be done for, you know, every point in the 3D world. And once we have this spherical image, okay, we lost the explicit information of the 3D world, right? As in the pinhole case or so. So understood what is a spherical image. We also understood a bit of how the image is acquired, and at least in the in theory. And now we need to understand how we can acquire it physically with a device. And once we acquire this image, how we can represent this image. Okay, so these two topics are discussed now. And first thing we need to state here is that there is no sensor that sees the whole scene. So we have this spherical imaging model that says everything in the scene is imaged to the surface of the sphere, and the surface of the sphere should be like a sensor, right? But we cannot physically design this sensor. So what we do? What can we do? We use actually regular planar silicon sensors, right, from regular cameras, and adopt optical solutions to project the all-around information to that sensor or some sensors, not only one. Okay. What are these optical components? Mainly lenses and mirrors. Okay, we can use both or some of them in different cases. And then, well, we have a small coverage of the scene by a combination of a planar sensor and well, an optical component. This is mapped to a part of the sphere by software, and then we can think on our spherical imaging on the sphere, actually. Okay. Well, we will review some capturing systems that are called catadioptric, polydioptric, and dual fisheye-based devices for acquisition. So here we have some examples, but they are most based on this dual fisheye system. The first capturing system that we discuss here is the catadioptric system, and we have a regular camera here, so a regular sensor, a regular camera, and also not very special lens. What we use here for capturing the whole scene information is a mirror, a convex mirror. Okay, so we face this convex mirror to the camera sensor, and this camera can capture all the horizontal information with this combination of devices. One problem of this system, the color dioptric capturing system, is that it doesn't cover the full field of view. So it covers the full horizontal field of view, or in other words, it covers the 360-degree field of view in horizontally, but it cannot cover the full 180 field of view, vertical field of view, because we have, well, the mirror and also the camera. So we cannot see throughout the mirror nor below the camera, right? Two other problems now of this kind of capturing device is that they are bulky, so we need well, a complex system here, and fragile because we have those mirrors. And well, it's not actually being used in current research or current industry, but in fact, this kind of sensor was used when this big omnidirectional imaging area emerged, like 20, 30 years ago. Well, once we do not cover the full field of view and we have this kind of occlusion, the mirror and camera or sensor occlusions, we can actually map the information that we can capture in a cylindrical form, and this will be, well, a different model of omnidirectional camera. Okay, that's not actually omnidirectional. Well, another system for capturing omnidirectional images is what we call a polydioptric system. And it is actually a collection of cameras that point outwards from the rig. So they are organized in a rig and point outwards. These cameras are actually regular cameras, as in the previous slide. And they have common lenses as well, maybe a wide FOV lens, a wider FOV lens than normal. But yeah, they are regular cameras. The main idea here is that each camera captures a narrow field of view image, so a common image, and these all these images can be combined using what we call the stitching or a stitching algorithm or a mosaicing algorithm that, you know, stitches those images together. And then we can cover the full field of view if you want. This kind of device is also bulky, and they are expensive because, well, we need lots of cameras. Here we represented these cameras or this rig as a collection of 6 cameras, maybe, but we can extrapolate this idea and have like 20 or 30 cameras. As much as we want. One of the advantages of using this capturing system is that they produce high resolution images, or they can produce high resolution images if you have, you know, good cameras capturing the scene. And also we can represent only part of the scene if you want. If it's not mandatory that we cover the full sphere. We can have a circular, we can capture only the horizontal field of view if you want, or the full scene, okay? Well, and then we have what we call dual fisheye-based capturing systems. And the idea of this capturing system is that we have only 2 cameras, each camera with a wide field of view lens. And this lens is actually called what we know as fisheye lenses. And each lens or each camera captures an hemispherical image. So it covers a bit more of 180 degrees in field of view. And this overlapping region that is covered by one camera and the opposite camera is used for stitching as well, as in the previous system. Okay. The main advantages of this kind of device is that they are portable and they are cheap. So we are talking about 2,000 reais. It's not too much, and you know, you can put in your pocket and walk away, and then you take a picture, put your pocket again, and that's it. The big problem of this kind of device is, well, as expected, they are not so high resolution devices. So they produce what we call here user-ended images. It's like 3K, 3.5K by 6K pixels. It seems a lot for regular images, but it's not too much when we're talking about full field of view coverage. Okay. Well, so we saw that there is no spherical sensor. We have some kind of combinations of lenses and mirrors or so. And once we capture the images, we map them to the sphere. And what happens now? Okay, we have a spherical image mapped to the sphere. How we represent this image, and how do we store this image, and how we process this image? Well, we are aware of different mappings, like sphere to plane mappings, and most of you might know some of these mappings. They are different here. We have some different kind of mappings. Some circular, other with a complex shape here, or, you know, not so familiar. Each mapping has, it preserves some properties when mapping the information from the sphere to the plane, and vice versa. And, well, they all introduce distortions. We can't go from the sphere to the plane without introducing distortions. They are not in the same space, right? So we need to know if representing the sphere on the plane is a good choice we can do, or if it's not. And we need to understand that this mapping will introduce some kind of distortion. Maybe we need to handle these distortions. Okay. Well, there is one mapping that I did not show you in the previous slide that we call, like in Portuguese, mapa mundi, or world map. This mapping function is actually called the rectangular projection of the sphere, and it is the standard sphere to the plane mapping function or representation. Okay, so we may agree that the Earth is rounded. Okay, it's the globe, and we commonly see the Earth, the world map, as a 2D planar projection. So what we learned many years ago in the school is that the poles they seem to be much bigger than they actually are. If we have the sphere representation of the Earth in our hands, we can move the sphere and see, oh, okay, the south pole is not so big as I thought it was. So the rectangular projection is actually known as a latitude longitude mapping, and it is actually very used or widely used in the scientific community and industry as well. So it's not we know the Earth as this kind of 2D mapping because it has some properties that are amazing for some kind of applications. So the sphere to plane mapping and the inverse mapping, the plane to sphere mapping, are both straightforward using the RP representation, but we have this irregular sampling on when we sample the sphere irregularly and map it to regular grid representation in plane. So this induces what we discussed before. The poles are highly oversampled. Okay. Well, just to understand a bit more of what this rectangular projection is, we can go back and see the image point here. It's a vector that has unit norm, so it lies on the surface of the sphere, and we can actually rewrite this point, okay, this point position, this pixel position, this image position, image information position, in spherical coordinates. So instead of using Cartesian coordinates like x, y, and z axis, like depending on this axis, we can actually rewrite this this point as this equation here. So if we pay attention of this equation, we will see that this kind of mapping is straightforward, and that these points that lie on the surface of the sphere can be represented using only two-angle information, so two-angle coordinates. Okay, so they depend on theta and phi, and we know that the spherical camera has, or as it's modeled, has a unit norm, so the R variable here is 1. So then my idea here is to switch our representation. Instead of using 3D Cartesian coordinates, we switch it to spherical coordinates. Okay. Well, we have shown this, mapping from this x point, but we have one point for every information in the 3D world. So we have a lot of these points, and we actually can map all the scene information in a regular 2D map. This 2D map has like a 0 to p limit in one dimension and 0 pi limit in the other dimension. Well, it's a continuous domain, and we need to discretize this domain and form our image. And this is done using this formula here, assuming that we have H pixels in height and W pixels in width. Okay, so we can map this whole scene information in a discrete matrix that stores all the scene information. And here we have a rectangular representation of that spherical image that was represented on the sphere itself that we saw before. Okay. Well, we know that the rectangular projection has some distortions, and these distortions are induced by this irregular sampling that we mentioned before. And this irregular sampling is proportional to sine of phi. So we can like see what this distortion means when we understand the portion of area on the sphere that is mapped to the plane, and we can compare these portions of area in this planar representation. And although it's not so clearly to most of you, I think, we know that as we are in the equator region, we have like a unit sampling, and as we move to the poles, we have a high oversampling, and then each pixel contributes to a small portion of area on the sphere, but a large portion of area on this planar representation. Okay. Well, we talked about the rectangular projection. That is one of these many choices we could use to represent the sphere to one planar representation, to one plane only. But it has some advantages. So it's straightforward, as you saw, and it's regular. We saw before that many other mappings can be used, but some of them are like a butterfly, or others are circular, and we would prefer not to manipulate this kind of shapes when you are dealing with discrete data. Okay. Well, we can actually map the sphere not to one plane, but to many planes. And the most common multiplanar sphere to plane representation is what we call the cube map projection. It's actually widely used in computer graphics, I think. And the basic idea here is that we can take our sphere, our spherical image, represented on the sphere, of course, and put it into I don't know, a cube that is tight enough to that sphere, okay, and map each of these each portion of the sphere to one face of this cube. Okay. Well, just for record, the cube map projection is also known as a skybox map. So each face of this cube will actually represent a portion of the sphere with 9 degrees, with FoV of 9 degrees. Okay. So the basic idea here is that we will squeeze that cube until it touches the sphere, and we use that middle point on each face to draw a plane, and then we project that part of the sphere to that plane. Okay, so this is what we call tangent plane projection. Well, the basic idea is the one that I just mentioned to you. Here we have some kind of animation. So we start from this sphere representation, and the cube is empty by now. Then we project part of its information to the one face, then the other part to the other face, then the other part to the other face, and then we have this cube map projection, this cube map representation. So what's the main advantage of using this kind of representation? The main advantage is that we have a little bit less distortion. So if you compare it with a rectangular projection, we see that, well, it's well behaved on the cube and not so well behaved on one plane as in the rectangular projection. What is the main disadvantage of this kind of representation? Well, we have, although we represent it here as one single image, we have actually 6 images to process, and these images are somehow connected, and we need to understand how these connections occur, and, well, depending on what we want to do, we need to somehow be aware of these connections and introduce some kind of processing in this connection, in the three plane connections, for example. So the cube map projection has this interplane dependence. We can extend this idea to many planes. So we do not need to use only 6 planes, as in the cube map projection, but we can use some polyhedra approximations of the sphere. And here we have like a nicosahedron that we call a nicosphere when it's when it matches or almost matches the sphere. But we have other kind of subdivisions here too, and these all can be used to represent the spherical information. The main idea of this kind of mood-plane representation is to mitigate even more those distortions that we saw before. And, well, it moves much more intricate. The connections between the faces are much more intricate as earlier. But it actually reduces the distortion. As I mentioned before, these kind of representations are based on successive subdivisions of a polyhedra, and we have as initial polyhedron like an icosahedron or an octahedron or so. Let's move on to the main challenges. Before, I just need to recap with you what we just saw. So we understood what are spherical images, then we understood the basics of the spherical imaging acquisition, actually. Then we talked about the devices, and then we talked about the representations we can use. Well, we have some challenges, of course, and we'll discuss some of them in the next few slides. So the first thing you may perceive is that we have a dilemma here. So we need to somehow trade off between context and distortion. So here we have a regular camera capture, as I showed you before. Here we have an rectangular representation of the same scene in the same position. And here we have one face of the cube map representation, also from the same scene in the same position. what we can see here is that, well, the smaller the FoV, the smaller the FoV, the field of view, well, the less the contextual information. So I don't know what we have behind this or you know, out of these areas imaged. But we have also less distortions. So as we increase the field of view, we increase the contextual information, and we also increase these distortions, regardless of the representation. So we are talking about the rectangular projection here, but we could use some of those other mappings that we mentioned before. The question is, are those distortions a problem? And if they are a problem, how can we handle those distortions? Well, we can go back and think about the classic image processing. And in the classic image processing, we assume that every pixel has some regular sampling, you know, in horizontal and vertical directions. And we can use some kind of filter that it's actually it doesn't need to tackle any kind of sampling problem, sampling issue. So it assumes that the sampling is uniform. And as we move to those other mappings here, we have these distortions that are actually induced by the field of view, adopted in that case. So we need to be aware of this, and maybe we need to tackle these problems in the future. Well, we will start our discussion on challenges here by recapping that the rectangular projection is the standard planar representation of 360-degree images. And as we saw in the previous slide, it has the full context, the full field of view, the full context, and a lot of distortions. And we also need to understand that the current image processing is made of, well, CNNs. Although we will focus on this kind of discussion here, we can extrapolate these ideas to perform like classical or traditional image processing based on some other kind of filtering and things like that. Okay. So when we talk about CNNs, we need to know now, or we need to remember that the kernels are the CNN kernels are by default regular. So they are like 3 by 3 or 5 by 5 or 7 by 7. And when we apply this kind of kernels, convolutional kernels, to our images, they cover uneven parts of the sphere. So if we are processing, if we are sliding a kernel window on the center of our rectangular image, we will cover one portion of the sphere if we, you know, map this kind of processing to the sphere. But if you have the same kernel on the poles, we are covering actually a much smaller part of the area of the sphere. So if you apply this kind of filters without proper treatment, we will have this uneven coverage, and we will end in like weighting the information in different, with different weights. We are weighting it uneven also. So an ideal kernel should adjust its support to address these ERP, these rectangular projections, which are at the end this kind of non-uniform sampling that we know how it behaves. It's proportional to sine of phi. So we need to adjust the support of the kernel to where it's been applied in the moment. Okay, in that moment. Here we have in this red image here, the upper image, we have a regular kernel represented in red. Okay, it's larger than usual, but it's larger to visualization purposes only. And here we have a kernel that addresses DRP properties represented in blue. So let's think that this image here is an rectangular image. Here we have a convolutional kernel or a filter kernel, any filter kernel. Here it's aware of the distortion. Here it's not aware of the distortion. Here it's aware of the distortions. Well, I don't know if you can see from there, but we have like a a belly here, but they are pretty similar to me, and this adaptation is worth or not. Well, we have here a kernel centered on the equator line, so it should not be so affected by the distortions, by the non-uniform sampling. But as we move to the North Pole, for example, we should adjust this kernel in this way. So this kernel is not anymore square, nor even close to square. Yeah, it has a complex shape that takes into account the spherical deformations induced by the rectangular mapping. So these regular filters are spatial. The regular filters are spatially invariant, have spatially invariant support that we are showing in the upper part of the image, and we need to make the or to force they to take these ERP properties into account. So one of them is this kind of adjustment as we move to the poles, and the other property that rectangular images have is that they are circularly connected. So if we are moving our kernel to the right, and then we touch the lateral board here, what we do in classic convolution, for example, is to perform padding, zero padding, or extrapolate information there and compute the convolution as it was not a problem. And that's it. But if we move to the ideal kernel in the rectangular image processing, we need to make some kind of padding as well, but copy the information from the other board. Okay, so we need to perform this kind of circular padding. Okay. Well, as I mentioned, the circularity issue can be solved by padding. So we can perform the padding manually and then process the information, and that's it. Or you can use some kind of module in operation. But adapting the kernels is a bit more tricky, because we have now kernel sampling points that need to be spread depending on the kernel position. Fortunately, we have some works that do this and perform this kind of adaptation and deliver this framework to further processing. And here we highlight what they call the dilated convolutions, distortion-aware convolutions, and deformable convolutions. The main idea of these three approaches is that the one that we just mentioned before, that is to spread those sampling points when computing the convolution over that ideal region or kernel support region. Okay. These approaches also perform this kind of treatment naturally, so we do not need to explicitly pad information here. We can just use these approaches to process the rectangular image. Okay. Let me think about what I was going to say. Well, don't remember. Well, that's it. So we can use regular filtering in the rectangular images, but they are not like correct from the theoretical point of view, and they will be weighting the regions of the sphere in different intensities. But we can address this problem using these three approaches and probably many others that employ similar ideas. We also have some kind of challenges when we process other representations. And I'm depicting you here, or I'm depicting the cube map issue here, where we have the central face, for example, and we can some kind of consider the information from the other faces when we are processing this particular face. So we can actually, instead of projecting the surface of the sphere to one face of 90 degrees, we can project it to a surface, a face of the cube that is a bit larger. So we can project like 92 degrees. Of course, it will introduce a bit more of distortion, but we have now an overlapping region that could be used to solve this kind of interplane issues. Okay, the same concept that I'm showing you here in the cube map case can be applied to the other multiplanar representations like the icosphere, as I mentioned before, noting that the triangles from that other representation will have, of course, other boundary conditions to be treated, but the idea of padding can be adopted as well. We mentioned some kind of mapping from the sphere to one or more planes as a possible solution. And in fact, as I mentioned before, the rectangular projection is the standard representation of spherical images. And why we project the sphere to the plane and not, you know, use another representation for it. The main idea is that we can use some old tools to process full field of view images with small or no, if we are like agnostic, treatments. So if we project, if we represent the spherical image on the plane, we can tackle it as an image and process this as an image, ideally taking into account this distortion or this kind of multi-plane dependencies. Okay, but one thing that we did not mention is that this spherical image can be actually represented in the graph, so in a spherical graph. Where each pixel is a node in this graph, and the adjacencies between pixels are encoded as edges. So if we represent this spherical image on a graph, we don't have any kind of topological issue, and we can perform graph signal processing without needing or with no need to tackle like special conditions. Actually can use graph neural networks and approaches like that to perform much of this signal processing. One problem of adopting any kind of treatment for spherical imaging processing is that, well, we have GPUs, and these GPUs are some kind of focused on tensor processing, where the information is kind of regular, and any kind of adaptation that need to map to deviate from that regular processing will introduce some kind of slowness. Okay, so these non-convolutional operations are, after all, demanding. Okay, non-conventional convolution operations. Well, actually, there are some works that make some kind of comparisons, and they say, well, it's not worth to use deformable convolutions, for instance, because at the end, our results with or without this kind of treatment were comparable. So, but the training time, the inference time, some kind of processing are much slower, and it's not worth. I think that's an open question, but we have some kind of works that are in this direction. Well, besides the sphere-to-plane issues, sphere-to-plane mapping issues that we mentioned before, we have other issues as well. Like from a dual fisheye camera, we have actually one capture like this one, where we have two hemispherical images. And when we move to this equirectangular representation, we have some kind of loss of information, right? Here we have an overlapping region. I'm not sure if it's clear to you, but for example, we have the stairs here in both images, and at the end we have one stair on. Okay. When we do this kind of processing, we will introduce some other or we miss some information. And when we move from the rectangular representation to the cube map, we will miss some other information. And when we move to the cube map to the rectangular back, we will miss information again. So we need to have a linear path here when we are coming from one representation and going to another. So it's one thing that we need to keep in mind when we are processing spherical images. When we have those multi-camera representations like polydioptric and dual fisheye-based systems, we need to stitch the different images together. And when we do this, when we perform this stitching operation, we will sometimes have these stitching lines. I'm not sure if they are visible to you, but sometimes we have different lighting in one view and another view, and it's not like equalized when we have the full image represented. So these stitching lines, they will appear in the same position, like here and here. All my images captured with the same camera and without further processing. And we can think that maybe these stitching lines will bias some kind of training or so on. Okay. Well, the objects have variable appearance depending on where they are in the image. I don't think this example is good enough, but we can think that me and Cláudio are not in the same position. So let's think that I'm closer to the camera. I will have some kind of distortions that Cláudio has not. So Cláudio is in the equator line, far from the camera. If I'm here, like on the side of, very close to the camera, I will have like a head that covers most of the North Pole, and maybe my hand will cover most of the South Pole. So this is one thing that we need to pay attention when we are working with spherical images, especially in, I don't know, detection tasks where we don't have a fixed appearance model for the objects. Okay, and another problem that may occur is that if we don't, if we get our camera and hold this camera like upright, we will have some kind of image similar to this one, where the horizon is aligned to the equator line. But if we tilt our camera in some direction, we'll have a sinusoidal behavior in our horizon. And this thing, this appearance will be so strange that maybe we cannot understand the image in the first moment. And this kind of misorientation of the camera can be, or can preclude further processing. So this is one of the tasks we selected for discussing a little bit more, and Cláudio will probably present this part in a few minutes. Another big challenge that we face in spherical image processing is the lack of benchmarks. So we know that there are many data sets for regular images and different applications. So we have annotations for detection, we have annotations for segmentation, we have annotation for, I don't know, whatever we want. We have additional data like depth, we have infrared, MAPIs, we have lots of data, when we are dealing with regular images. But this is not the case, unfortunately, for the spherical area. So we have like a very new area, and we don't have any textbook, for example. We don't have big data sets. We don't have sufficient annotation for many tasks, and it is still a challenge to get data for training like a deep learning model, and also it's a challenge when we are comparing methods. So there is no there is no consensus that the metric A is better than another metric, and it's complicated to compare different methods and different applications using spherical images. We hope this change in the next few years, and the area can be better explored. So now I think Cláudio will follow this presentation, and we will discuss next 3 selected applications that appear in this field. So, Cláudio.
So, thank you, Thiago. Maybe I'll just share the screen. Okay, just a moment. Let me just find the share screen button. Share screen. Okay, can you all see the screen now?
Yeah.
Good. So, hello everybody. Good morning. Actually, it's middle of the morning now. Thiago mentioned several aspects regarding capture, representation, and processing of spherical images. And as you could see, basically any application that involves pinhole images can be extended to spherical images as well. So if you think virtually any application like object classification, image classification, object detection, segmentation, all those applications that are typically explored by pinhole cameras can be extended to panoramas. Maybe the transition might not be straightforward, but they can be. In this presentation, we selected applications that mostly benefit from the full field of view of spherical cameras. And as Thiago mentioned, we will focus on 3 main applications, and hopefully I'll be able to convince you that spherical images are suitable for these applications. So the 3 applications are gravity alignment. So this name might sound weird for those of you who are not used to this naming in spherical images. But as Thiago mentioned, basically the idea is to align the image, the spherical image, the equator of the spherical image with the horizon in the real plane. So this is usually important when you have still images that you want to have aligned panoramas. And if you have video sequences, you have a kind of stabilization of the panorama. The other application is layout and depth estimation. Actually, they are very related applications. And basically, layout means recovering geometric structure of a typically indoor room or scene. And although you can try to do this kind of application with pinhole cameras, you must have several captures to cover the 360 field of view, and you have to stage them. And in theory, all this information is encoded in a panorama, in a single panorama. And if you can get either the layout or the 3D, per pixel 3D information of the scene, you can have an idea of the 3D structure of the object, and you can do it, you can export this information for like metaverse navigation, AR, MR, VR experience with head-mounted display. You can perform view interpolation and generate stereo pairs and provide a real 3D visualization of the scene with a degree of freedom in the head. Of course, for self-driving vehicles or robot navigation, it's very important to have 3D information, depth information for either detecting obstacles or SLAM in robotics. And the first application that I'm gonna briefly describe here is gravity alignment. Just to clarify, the goal here is not to get into details of different approaches that handle each of these applications. As Thiago mentioned, given a spherical image, you can represent it as a ERP, which is typically called a panorama, cube map. You can have icosahedral representations, and I'm not gonna get into the details of the representation, but the problem itself. And for each representation, if you're going to the deep learning pipeline, you need a backbone, and this backbone might use conventional CNNs, might use spherical adaptations, might use attention models, right? So it's a kind of plug and play of several different components. The input, which is usually we do not have control. I mean, you get the image. I don't know which kind of camera was used to capture it, but you have control on the representation and, of course, on the technique itself. So basically, as Thiago mentioned, a 360 image basically is a projection of the scene onto the sphere. So if you don't consider sampling issues, these images, like the analogic spherical images, where you don't have sampling, they have 3 degrees of freedom. You can rotate it around the center of the sphere, and still you have exactly the same representation. So any capture of a spherical image can be rotated or derotated to a standardized capture setup. And when we talk about gravity alignment, basically we want to align the equator line of the panorama to the sphere, the spherical projection, with the ground plane. So if you have an unconstrained capture setup where you can have rotations, the goal of gravity alignment is to basically derotate, to estimate the rotation angle, and then rotate this image back to this standardized canonical point of view, right? And as an additional motivation, as we're going to see later, if you have applications such as layout estimation, that you get into a room and you put a spherical camera. Usually this spherical camera is already placed so that it produces a gravity aligned panorama. And these kind of constraints are usually explored by methods that try to perform layout decimation. So if you have an unconstrained capture setup, you can use the derotation as a pre-processing step for other applications. One small detail is that in theory, any rotation on the sphere can generate any two captures that differ only by rotations can be warped into another by just rotating the panorama. In practical applications, this is not true, because when you have any kind of representation, so I'll assume that the ERP is the default representation here, as we are seeing here. Since you have sampling issues and the poles are much more densely sampled than the equator line, if you rotate an image so that the equator turns into the pole and vice versa, you're going to switch which region. Some regions are going to be upsampled and other regions are going to be downsampled. So there are some interpolation issues that must be also taken into account when rotating a panorama. So basically, that's the visual representation of an aligned image. Probably the image in the bottom is going to be very hard to understand for people who are not used to seeing spherical images. It's highly distorted. But the first scene, the top scene, is probably more plausible for understanding. So you can see a classroom, you can see the blackboard right in the middle, you can see the desks, of course you can see the floor, you can see the floor on the bottom and the ceiling on the top. If you have a rotated panorama, rotated capture, all these informations are messed up, right? So the main goal of gravity alignment is to warp the bottom image, to rotate it, to find the rotation angle, and generate the top image from the bottom one. And basically, the second image can be viewed as a rotated version of the first one, and you want to derotate it. And there are several strategies for doing that. You can basically perform feature matching, and if you know that the gravity is aligning all the images, you can reduce the possible number of matches and poses. And this is related to depth estimation, as we are going to see later. So if you just have one capture, what can you do? The idea is that you can handle the gravity alignment problem as a learning problem. So basically, you have in the training set, you have either a pair of panoramas, one in the upright position, which means it's already gravity aligned, and you can artificially generate rotated versions. So if you have a set of images that are already gravity aligned, you can generate a set of artificially rotated images and then generate pairs of rotated and derotated images from which you can estimate the rotation angle. So basically, that's the core of these strategies that use single panoramas for gravity alignment. And basically, the problem is to find the upright vector, which is equivalent to finding the rotation matrix that can transform the first image, the rotated image, into the gravity aligned one. And there are several technical details on how to encode the rotation and how to encode the angular information of the rotation, which might be kind of a small detail, but they do have impact on the design network, specifically when you talk about angular information, because you have the circularity issue. I mean, a rotation close to 0 degrees is very similar visually to a rotation close to 360 degrees. And if you, depending on how you design the loss function to train your network, if you use direct L1 or L2 norms, of course, that 0 degrees is very different from 360. And you can tackle this problem as a classification problem. I mean, you have a set of predefined upright vectors, and you want to see which one the image better adheres to, or a regression where you directly regress the regression angle, the upright vector. So here we have some examples of different upright alignment or gravity alignment methods, and the input image are the ones on the top, and the upright corrected images are the ones in the bottom. I mean, these are mostly nice results. I mean, you can probably recognize the scenes from the bottom views. From the top views, not that much, particularly the first two ones where the angular distortion is very high, and it's not easy to recognize what the scene is showing us. For me in particular, the second one is very hard to understand what's going on from the rotated version. So the second application that I'm going to talk a little bit about now is layout estimation. So although 360 images, they do represent the whole field of view, the 360 field of view, these images, they do not provide depth information, right? So the main goal of layout estimation is basically to recover a simplified 3D representation of the scene. So when we talk about layout estimation, we are typically talking about indoor captures, and more than that, in kind of structured environments. So many papers and applications related to layout estimation, they are related to virtual tours of houses and real estate agencies. And the idea is that you can get into a room, you take a single capture with a spherical camera, and then you can recover basically the walls, the ceilings, and the floor, and generate a 3D view from the environment. So what kind of information is required? Basically, what you want to find lines that connect orthogonal walls or walls and floors and ceilings, which relate to joints and corners in the image. So you can see the red dots on the top images are the corners that connect the four walls in the scene to both the ceiling and the floor. And as you can see, these lines that relate to the connections between the walls and floors / ceilings, they are straight in the real world, in the 3D world, but when you project to panoramas, they are curved, as you can see here. So different layout estimation methods, they handle different geometries. So some constraints are, the first one basically is a top-down view from a typical room. This is very common in houses. This is a cuboid. Basically, you have a cuboid representation of the scene. The second representation here is a Manhattan room, a Manhattan layout, in which you don't need to have a cuboid, but if you take a top-down view, basically all the connections are orthogonal. And there is the Atlanta assumption that basically you have walls that are orthogonal to the plane, which is usual in most applications, but you can have like curved walls. You don't need to have either cuboids or orthogonal connections between the walls. And of course, that if you have a cuboid assumption in your model and you run the inference in another room that violates this hypothesis, the results are going to be nonsense. On the other hand, if you have a very generic model, such as the Atlanta model, and you run it on a cuboid, it should work. But usually, if you have a model that's too generic for a given application, the results are going to be worse than those that are designed for that particular kind of layout. So before deep learning, there were some approaches that try to do a single layout estimation from a single panorama. And basically, they were based on primitive extraction. So geometric primitives are lines, are corners, and which is what we expect in a typical layout. And nowadays, in the past, say, 5 years, that's not what I wanted to say yet. Still in older methods, the ERP representation was the most popular, in particular because you have a single planar image that represents the full field of view. If you have cuboid representations, then actually you have a set of 6 planar images, and you have to deal with the connections between the faces of the cube, right? And as I was mentioning before, some methods, they regress the room walls, ceilings, and walls, and the joints between the connections, the walls and the floor and ceiling. And other methods, they basically, they recover the lines that connect, that comprise the connection between the walls and other walls, walls and ceilings, walls and floors. So, of course, if you have all these lines here, all the connections, you can get the corners. And if you have the corners in an ordered way, you can get the connections. I mean, this corner must be connected to this corner, and this must be a straight line in the panorama, and so on. So basically, it's a question on how what kind of information you want to obtain from the image. So here we show some results that try to provide different information that in the end generate the full layout. So an example from 37, it's an approach that basically wants to obtain the corners of the junctions between the walls and ceilings, so different planes that make the structure. This is a more generic example based on Manhattan worlds. So basically, you can get all the lines that connect the corners in the layout. This is another example of layout estimation in which you explicitly define the region that relates to the ceiling, to the ground plane, and to the walls. And finally, just all these methods, they usually they are able to generate the 3D representation as in the rightmost images, but they have different assumptions on the layout, and of course they vary based on the kind of backbone that is used, of course the parameters that must be regressed, and so on. So basically, that's the final goal of any layout estimation approach. And as you can see here, it's important to have an input image that is roughly aligned with the equator line, because we expect the ceiling to be close to the North Pole and the floor around the South Pole. And all the walls should be around the equator. If you rotate these images in an arbitrary angle and run these methods, the results are going to be usually very bad. Some methods explicitly assume a gravity-aligned image. Some approaches, they say that it's good to have it, but if you have a very strong angular distortions, the results are very bad. So still going further into the granularity of the application, of course, that layout estimation provides some kind of information about the 3D structure of the scene. But basically, it provides information about the walls, the structure of the environment. If you are in my room, you can see in the background, this is a kind of kettle to warm water. This is not going to be captured by a layout estimation method because it's not part of the layout, it's an object. So layout estimation methods, they provide a rough representation of the 3D scene, and they are restricted for indoor environments. The goal for depth estimation methods is to obtain typically a dense map where you want to know the depth of each pixel in a panorama. So if you have depth information, of course, you have a much richer description of the scene, geometric description of the scene, right? As you can see in this example here, you can see all the chairs. These chairs, they are not important for layout estimation, but of course, they do matter for depth estimation approaches. And you can have methods that explore a single image, a pair of images, which is the classical stereo setup, or multi-view. So, what do you need to estimate depth information? For those of you who are familiar with the basics of computer vision, you know that if you have a stereo capture with a calibrated camera, you can have the disparity and the depth of each point that overlaps into the field of view of the two captures as the human eyes, right? And I'm not getting to the mathematical details, but basically you can have all the theory behind the epipolar geometry. And when you deal with panoramas, the main difference is that you don't need to deal with intrinsic parameters. So basically, you just need to recover the extrinsic parameters which relate to rotation and translation of the camera. So basically, the core concept in 2D depth estimation with spherical cameras is to estimate the essential matrix from which you can recover the pose, and given the pose and correspondences, you can estimate that. If the cameras provide some kind of alignment, as in the gravity issue that the gravity alignment problem that I mentioned before, then you know that the displacement must be in a certain direction, and then you can explore these constraints to improve the matching process, which is required to refine the pose and get the correspondences for depth estimation. And typically, you can perform sparse correspondence matching, then you're going to have a sparse depth match, or a sparse depth map, or you can have a dense feature matching algorithm that will provide you dense correspondences, and then you can have a dense map. Right? So this is an example. Basically, it's actually it's a joint work by me and Thiago, and it's not based on deep learning. It's based on classical vision tools. The idea is that you have several captures of an indoor scene, and basically you perform an initial alignment of the images. You perform sparse matching for pose estimation, and then refine it with optical flow, which provides dense correspondences, right? And there are small details like adaptations of traditional vision models to deal with the spherical setup. And in the literature, you see that single view methods are becoming more popular. And one main reason is that, okay, you need just one view. If you need just one view, why getting more views? And again, the core idea is that you have a deep learning approach in which you have the input image, the RGB image, and you have a depth map that will be used to train the model so that when the network sees a new scene, it will be able to generate a depth map that hopefully is coherent with what is expected in real life. So the idea is that when you have talking about convolutional networks, you have the support of the kernel, and it implicitly increases when you perform pooling operations, which means that you, as you go down in the network and you decrease the spatial resolution of the layers, a same kernel, say 3 by 3, it actually has a larger effect on the original domain of the image, and you see more context. So that's actually the rationale for using deep neural networks for getting depth maps from single panoramas. Still, there are some approaches that use cube maps, some approaches that use ERP representations, some methods that kind of use both representations, but still ERP is the most common because you have a single image, planar image, and that's all you need to generate, to go back to the sphere and to process the depth map. So I'm showing some examples of different single panorama depth estimation approaches here. They are rendered in different color maps because they were extracted from the original papers. But overall, you can see what's going on. I mean, if you represent here the gray value as the depth, you can see that the beds, the beds, they vary the depth, of course, but you can see that the wall is farther from the camera than the beds. You can see that this door here in particular is the farthermost object in the scene, and it correctly is marked as a brighter region, right? This is basically a similar example, but with a different color map, as well as the third example. And here you have a kind of layout estimation obtained from the depth map. As you can see, it's very noisy here, which is actually expected because the depth map is going to have noise. It's going to contain noise. So if your final goal is to get only the layout, it's pointless to get the point-by-point depth estimates and then just project it to a top-down view. You're going to probably introduce distortions that are not plausible in the model, such as these curved walls here. So I think that Thiago can join me here in the end, in the final remarks.
I'm here.
Hi, Thiago. What can we conclude? Maybe Thiago can get back to the presentation.
Okay.
Oh, yeah. Oh, I'll just fast forward the slide and you can talk a little bit.
So I think the main conclusions that we can get here is that, panoramas are popular, and as Cláudio mentioned, virtually any application can benefit from it. There are some issues that we discussed in the main challenges section. So we need to think about some decisions we made when we were thinking about traditional or pinhole-based image processing, and maybe we can or we should adjust those algorithms to explore the correct geometry of those signals. And one final issue that we can recap here is that, well, we still need some data sets, and we still need some metrics to evaluate different methods to, and without this kind of resources, we cannot advance these areas. I mean, with the same precision or with the same the same, I don't know. We need to have those benchmarks to advance the area with success. So I think that's much more to come. And this talk was meant to introduce this topic to those which were not aware of spherical images. But of course, we have a long path to come. I don't know.
So, yeah, so just I'm going to show the references. So probably this talk is being recorded. I'm not sure if the slides are going to be made available, but well, just slowly go through the references. And of course, you can see there are several references from the past, I don't know, 3-4 years. And if you take a look at the image and image processing and vision conference such as ICIP, CVPR, ICCV, CCV, you're going to see several papers that either present a new method or a new data set for panoramas. So I think this concludes the presentation. Thank you all for the patience and for attending. And now I think that Cláudio can, or Manuel can take over.
Yeah, so thank you, Thiago and Cláudio, for the nice comprehensive tutorial. Very nice. We have time for a few questions, so I would like to encourage the audience to come by the microphone and ask questions. For the moment, we have a brief question here from Bruno Borges. Is asking what is the format that you can save those 360-degree videos?
Thiago, okay.
What is the format we can save? Actually, the camera will probably capture those images using one of the capturing systems that we discussed before. So the camera will save in the device itself, like two spherical images, for instance. But we can export these images to the format we want, like cube map or like rectangular or so.
Yeah, but it's an MPEG is what?
Oh, okay. Yeah, probably for the images we have JPEG, and for the videos we probably have AVI maybe, or MPEG. I don't know. I'm not sure. It probably depends on the company that produces the device.
Okay, so while people get ready to go to the microphone and ask questions, I'll ask a few questions of mine. So one issue, an important issue that Cláudio pointed out is this thing that he called gravity alignment. One observation is that if cameras had some sensors like say geomagnetic field sensors or maybe accelerometers, this could be easily solved by saving this information as part of the metadata of the image. Is that already available or not?
Yes, some cameras do have it already.
Okay, so then you can export this. Great.
Exactly.
So
yeah.
Another thing that I mean, you guys mentioned is are the issues regarding convolution. I mean, you have to perform circular convolution. the density of the sampling varies across the image and so on. And then at some point, Thiago pointed out that performing convolution on graphs, I mean, using, graph CNNs is probably at this moment the most general solution to this issue. Is that correct? And then what are the implications in terms of performance for applying neural networks to spherical or spherical image, 360-degree image?
Yeah, so performing graph spherical processing is not, it doesn't depend on the topology of the signal, so we do not need to explicitly tackle those sampling issues and the circularity problem. There are some solutions. I remember one that aims to recover the upright vector from the images. I'm not sure if we reviewed some solutions for the other two applications. I'm not sure if Cláudio remembers.
Yeah, but my question is, I mean, how hard is the performance sort of affected? Because you have to do this on a graph. You can't just perform regular, convolution, linear convolution as you do in regular images using CNNs.
Okay, so maybe Thiago, just make a brief comment here. There are like pros and cons for that. One nice property of exploring graph convolutions is that you can resample the sphere and you don't need to have the oversampling on the poles, right? I mean, you can, in theory, the pole collapses to a single point, but it's represented as a line in the ERP image. And if you move to graphs, you can resample it and you have less samples, right? On the other hand, please, anybody in the audience, correct me if I'm wrong, because I'm not aware of the state of the art, the advances in graph convolutions or other kind of graph neural networks, but they're still considerably lower than convolutional networks, traditional networks. So this is a kind of trade-off, right? And if you see the applications, some papers, they do say, okay, you can use networks that are specific for spherical images, such as, and then they mention dilated convolutions, deformable convolutions, or even graphs. But in the end, they say, but we use the planar network here. So I don't have a concrete answer to your question. And actually, in my personal opinion, it's an even more generic question of choosing a given backbone for a problem. Maybe it works better for this data set, but it doesn't work as well in the other data set. So I think I'm raising more questions than answers here. But I'm not sure if Manuel's satisfied, but...
No, I'm fine, thanks. Yeah, so how about, I mean, have you guys or the community working with 360-degree image have thought about maybe considering performing 1D convolution, I mean, 2-pass 1D columns and rows, or rows and columns? Because by doing this, when you're dealing with the equator, you could use some kernel size, 1D convolution along the lines, and then as you go towards the poles, then you could be keep increasing maybe linearly the size of the kernel. Would that help somehow? First of all, is this convolution separable, right?
Yeah, so actually there are some approaches that kind of do that. I mean, they do a convolution. They basically collapse the panorama into a line, because along each, let's say along each row no, not sorry, along each column of the ERP, the sampling is roughly constant. The main problem is along the rows. So basically, they collapse this the 2D image into a line, and then they propagate the information along the lines using, I don't know, recurrent networks or attention, right? But this idea of having deformable kernels, we actually have used that, but not to train the model, but to filter a panorama. So the idea is exactly that you can adjust the bandwidth of the filter depending on the height on the row index. But separable convolution, Thiago, have you seen that? Some papers that do explore explicitly separable convolutions?
No.
That might be actually an interesting point to investigate. So there is one thing that actually we are doing right now is to perform different convolutions in parallel. So for the same image, you convolve the input image with the same kernel with different dilation parameters, and then you combine this information depending on the latitude of the image, depending on the row index of the image. I'm not sure if that's clear, but
okay,
it's kind of in the line of what Manuel said. But basically, that's done in parallel. I mean, you do all the convolutions in a same batch, so you have several supports, and then you combine this information later. Instead of having one kernel for each line, you have all the kernels for all the lines. And actually, the filter is the same. You just change the dilation factor, right? It's not a different kernel for each line, which is actually an issue, right? Because you don't, maybe having one different filter, one different kernel for each line might not be the best idea, since you want the filters to be related somehow. You just want to change the support. So you can do something like that by doing dilated convolutions.
Okay, we have reached our time limit here. I would like to thank again Professors Thiago Silveira and Cláudio Jung for the nice presentation. And I would like to invite the audience to join me and thank them for their work.
Thank you.
Thank you.